Yeah, let me begin with a short motivation about entanglement. So entanglement is arguably like one of the most fundamental non-classical features of quantum mechanics, right? And its effects are ubiquitous. I mean, they are visible everywhere from all sorts of different quantum information theoretic protocols. So in its most vague or basic sense, intuitively, we can think of entanglement as a property of two objects, as a global property of two objects, which cannot be defined in terms of the local properties of the sum of the parts, right? And in other words, if they are two separate particles who are spatially separated, if you do something on one of the particles, it will affect the other one in almost instantaneously. So that's what the physically we can think of entanglement as, like some kind of a connection between the two particles, which cannot be explained by just the local properties of the two particles. So in the sense, the sum of the parts does not suffice to explain the entire global system. And perhaps the most basic use of entanglement is in something called quantum teleportation. So let me just quickly describe it to give you a feeling of what do we mean by entanglement and what can be done with entanglement. So as you can see, we have three particles here. Let's say the first two are in possession of Alice, and the third one is in possession of Bob. If you're overly patriotic towards India, you can think of some Indian names for them. I don't know, like Anamika or Bholela or whatever. Let me just stick with Alice and Bob here. And so the point is that Alice, the second particle of Alice, is in some sense entangled with Bob, let's say, right? We don't know what it means, but we can think of it as some kind of a connection. There's some kind of a connection between these two particles. And the task for Alice is to transfer the first particle that she has, the state of the first particle, to Bob. And since the second and third particles are somehow entangled with each other, Alice can do something on the two particles that are present in her lab, and then a protocol can be devised which kind of transfers the state of the first particle to the particle of to the lab of Bob without any kind of a physical communication between the two. In the sense that whatever Alice does, it happens in her lab only, which is spatially separated from Bob. And since there is a pre-shared notion of entanglement between Alice and Bob, which is between the second and third particles here, that kind of transmits this information that Alice wants to send. So this is like very naive description of teleportation. I just wanted to bring it up in order to give you an intuition of what can be done with entanglement and what are its practical uses. But if we want to use entanglement as a resource, we first need to understand whether we have entanglement in our possession or not. In other words, basically, if you have two particles and if you know completely their state theoretically, then the question is, can one decide whether there is entanglement present in those two particles? And once we decide that, we can then think of how can we use it in various kinds of physical applications, right? But it turns out that this is a very difficult problem. Even if you have complete knowledge of the two particles and complete knowledge of the global state of two particles, the problem of determining whether or not the state contains entanglement is tremendously hard. And there has been a lot of work done in this realm in the past few decades, but still it is quite open, and there is no effective algorithm that can be applied to deduce whether or not any given state contains entanglement. And that is where I come in the sense that I devise a simple protocol. You can think of it as a protocol, which is very different from the usual methods that have been applied to detect entanglement for the past few years, right? So what we'll learn about in this talk is.
Can I ask a question?
Yeah, sure.
So I can imagine that. So the complexity of determining whether a given state of, let's say, two particles is entangled or not, should depend on the dimensionality of the Hilbert space in which the two particles are living, right?
Sure.
So how does the complexity scale? Is it exponential or is
Yeah,
it?
so it's exponential. So basically, it increases exponentially with the dimension of the system that you are concerned with. And so, for instance, for qubit systems, if you have two qubits, then basically the problem is very easy in the sense that a nice solution exists. But as soon as you get to 3 dimensions and as you increase the dimensions, then the complexity of the problem of determining whether any given state is entangled or not, it's exponential in the dimension, the
Okay,
time required.
do you know if a quantum algorithm exists whose complexity is not exponential?
Huh. I I'm not sure, but I think it does not exist as of now. But
Okay.
I might be wrong. So this complexity. I should mention that this is classical complexity in the sense that this algorithm that we have devised, or whatever algorithm you can think of that can be employed on a classical computer, this will take exponentially large amount of time, where the exponential scales with the dimension. And
Okay.
so even though there exists algorithm which will terminate in some finite time and will be able to tell us whether or not a given state is entangled, but the time required in order to do so will scale exponentially with the dimension of the system. And hence it might be, well, it might be the case that it might take, like the longer than the age of the universe in order to determine whether two particles are entangled or not. So it's not really useful in that sense. But I am not aware of, I don't think that it exists at the moment for quantum algorithm, but I might be wrong. So please take this with a grain of salt. All right. So as I was saying that I will in this talk, I will present a very unique connection between two very different mathematical objects. On one hand, we have entangled density matrices or quantum states. And on the other hand, we have graphs. And these are basically just networks, bunch of points in the plane or space and connected by some lines. You can think of it as a network. In maths, they are called graphs. And it turns out that there is a very deep connection between these two wildly different mathematical objects, and the properties of graphs can be employed to detect entanglement. And that is what I'll be talking about in this talk. So
Satvik, just one thing
yeah,
before you start. I just wanted to know, is the idea similar to Bob Koch's work? Do you know Bob Koch? He did this quantum picture formalism. So should I have that in mind, or should I just forget about it?
Yeah. So no. So that's like a graphical picture. That's not really specific to entanglement. That's like a graphical language in order to describe quantum mechanics.
Yeah.
And I will not be using that.
Okay.
It's very easy. It basically is helpful when you have to deal with tensors which have lots of indices, and it is complicated in order to deal with the I, J, K, L, and so on, indices and so on. So instead you talk about boxes and wires and stuff, and we can develop a nice graphical theory to describe all of the linear algebra or the basic mathematics that underlies quantum mechanics. There are categorical theoretic, I don't know how to say it, category theoretic aspects that come into picture, but I'll not be delving into that. This is different from that. This is not a tool in order to explain the mathematics. This is like you employ graphs which are not the same as the boxes and wires that
Right. Okay.
you're talking about. So in that sense, it is.
Okay.
I hope. Yeah.
Yeah.
Okay, so let me just tell you about the outline or the approach that I'll be taking. So usually when physicists talk about entanglement, they try to motivate it, let's say by introducing the EPR paradox or Bell inequalities, right? They try to give some intuitive picture of what it means for a particle or for two particles to be entangled. And there's certain merit to that approach. But here, what I'll do is I will try to present this theory from the very basics. So in the sense that the mathematical fabric of quantum mechanics, from the very foundations, I will try to convince you that this notion of entanglement pops out very naturally from the underlying mathematical structure of quantum mechanics, right? And so the first part of this talk is basically going to be an introduction to entanglement theory. I would say a mathematical introduction to entanglement theory. And we will always be dealing with finite dimensional Hilbert spaces. So in infinite dimensions, things get a bit messy and complicated. So I'm not going to go into that. And we will exclusively deal with finite dimensional systems. And here I just start with some basic notations. So for us, all
Hello?
we will only consider. Yeah, is there a question?
Yeah, so could you just introduce us to Hilbert space like informally?
Yeah. I will do that here in this slide.
Yeah.
So basically for us, Hilbert's complex Hilbert space is just a set of d tuples of complex numbers, right? So and in physics, usually Dirac's bracket notation is used to denote these vectors. So basically, a typical element of our Hilbert space is going to be like this. So we have just a bunch of complex numbers collected together to form this column vector, right? And the conjugate transpose of this vector will be denoted by as a bra vector like this. And basically, this is just you transpose this column and take complex conjugation. So this will be like a row vector with where entries are basically just conjugated, right? So this is our notation for vectors. So these are typical elements in our Hilbert space, which is basically just complex number to the power d. So basically we have just d complex numbers collected together in a column, and all possible such vectors are collected in this Hilbert space. So for us, this is the Hilbert space. It's a collection of all d tuples of complex numbers, right? And this set is endowed with the usual addition. So you can add two vectors by just entry-wise adding the complex numbers, right? You can multiply these vectors by a constant. So for instance, oops. So for instance, you if you multiply by lambda, you get entry-wise lambda everywhere and so on. So this is a vector space in that sense. You can add stuff, you can multiply stuff by numbers, and there are different distributivity and all those laws that hold. I'm not going to go into the picture or into the details of that. And this is basically the introduction. This is basically the bracket notation. And the standard basis of every vector space has a basis, right? So for instance, if we talk about just qubits or d equal to 2 space, we have two basis vectors, which is basically just 1, 0, and the second one is just 0, 1. And any vector in this space can be written as a linear combination of these two. So this can be written as v1, 1 plus v2, 2, right? And so on. So this is the standard basis of our space. And the inner product, so this is again another crucial property of Hilbert spaces. Hilbert spaces are endowed with this notion of inner product. So basically, if you look at this notation, on the left, we have this bra vector, right? So this is basically the complex conjugation here, right? And we have a ket vector on the right. And this is again like this. And this is then just matrix multiplication. And you just add stuff up and entry-wise, right? So this is the usual matrix multiplication here. And so as you can see, this in the first entry, this is anti-linear in the sense that we have a complex conjugation here. So if you add lambda here, this lambda will pop out as lambda bar, and linear in the second argument, and all the usual properties of inner product hold. So now we can talk about linear operators on the space, and they are nothing but matrices. So you can take a column vector and you can act on it by a matrix. So this is a d cross 1 vector, and a d cross d matrix acts on it to give another column vector, right? And so in that sense, the collection of all d cross d complex matrices forms the space of all linear operators on our Hilbert space, right? And again, this is again a vector space. We can define a nice basis for this. And again, this is called outer product, and we can again interpret it by our column and row notation, right? So for instance, I in qubit system, let's say if we want to write down this 1, 1, right? So this would be like 1, 0 and 1, 0 again. And now notice that this will be a 2 cross 2 matrix with just a single entry here, right? And similarly, you can do this for 1, 2, 1, 2, 1, and 2, 2, right? And any matrix, a 2 cross 2 matrix, can be written as a sum of the entries and with the corresponding basis vectors, right? So this ij, the outer product, this denotes the standard basis of our matrix space, right? So everything is nice and simple till now. Now, in order to talk about entanglement, we need to talk about bipartite two-party systems, right? And in order to do that, we need to introduce the notion of tensor products. So basically, this is like a generalization of multiplication of real numbers or complex numbers. two vectors, vector multiplication in a sense. So what we do is we have two vectors, they lie in different spaces. The first one is in CD1 and the second one is CD2. And the tensor product will lie in a larger space, which will have dimension D1 times D2. And how is this operation defined? Let me just illustrate it with two like qubit vectors, right? D equal to 2. And basically what you do is the result will be a 4x1 vector, right? And the first entry would just be V1 multiplying with W1 and V1 multiplying with W2, and similarly the other two, right? So basically we are just connecting them like this in this fashion, and then this is the product, this is the result. And this is the operation where we take two individual vectors and multiply them. We can extend this notion to the tensor product of two spaces themselves. So here on the left, we have one Hilbert space and the other Hilbert space with dimension D1 and D2. And we define the tensor product of this space as, so first what we do, this is a collection of vectors of this form. So in qubit case where D1 and D2 are both equal to 2, this will have elements like 1, 1. So 1 tensored 1. Let me just be precise here for a moment. 1 tensored 2, and so on. So this will be 4 vectors here. And by span, I just mean take all possible linear combinations of these vectors. And so in the qubit case, you can imagine that when D1 is equal to D2 is equal to 2, then these basis vectors will basically be nothing but the standard basis vectors of C4, right? This will be like 1, 1, this will be 1, 2, and so on. And when you take the span of them, you'll get nothing but C4 again. So this will be a space of four tuples of complex numbers, right? So this is our definition of tensor product. And so we can extend this to matrices as well in a very similar way. And so now if we have a D1 cross D1 matrix and D2 cross D2 matrix, we can define the tensor product. Let me just quickly illustrate it for 2 cross 2 things, right? By the way, there's no physical or insight into all this. This is just mathematical definitions, right? So when I say that, and I write this colon equal to, this is how we define stuff. So this will, as you can imagine, this will be a 4 cross 4 thing. And how we do it, we on the first block, we take this A1 and then multiply it to all the 4 elements here. And so this will be just A11, and I'll just write B for this entire matrix here. And similarly here, it will be A12B, A21B, A22B. So these are, the blocks are 2 cross 2 matrices themselves. So you can think of it as a block matrix where each entry is like a 2 cross 2 matrix, right? So this is our definition of tensor product of matrices. And similar as before, we can define the tensor product of matrix spaces themselves. And what we do here instead, we on the first slot, we take the basis vectors, basis matrices for MD1. In the second slot, we take the basis matrices of MD2. We take the tensor product in the fashion that I earlier described. We collect these all products in the set, and we take the span of this in the sense that we take all possible linear combinations. And again, for instance, if you take M2 tensor M2, you will basically get M4 again, space of all 4 cross 4 matrices. Right, so this was just basic linear algebra and basic notation that we'll use throughout the talk. And let me now come to the basics of quantum mechanics in finite dimensions. So,
Satvik, do you want to wait a second to just check if there are doubts? I mean, because you just finished our whole.
Just stop me bluntly anywhere. I don't mind at all. So, do you guys have anything about the notation and the tensor products and so on?
You went through a little bit too quickly for me, but I guess that's also because I'm.
So yeah, I can elaborate which part was not clear.
So when you went from vector spaces, you made a product of that. After that, you went through doing the same thing for matrices. I didn't quite get. So how important is it that I follow exactly what index goes where? Is it fine if
so it's important. So let's say, so you understand this, right? So we have two matrices here and 2 cross 2 matrices, right? And so for instance, you take the first entry of the first matrix and you just combine it with all the 4 entries of the other one.
Oh,
And then you put this entire thing in this first block here.
oh, okay, okay. I see.
Right. So here, for instance, first one in explicitly, the first one would be like A11, B11, second one would be A11, B12, and so on.
Okay.
Right.
Okay. Cool.
And you do this for, so this
All-
was the first block. For the second block, you take A2. So A12 will come here and so on.
I see.
And this is for matrices. So we have concrete matrices on left and right, and we can multiply them in this fashion to get a larger matrix. And then when you do that for basis vectors, so for instance, I think it would be insightful if I just take the tensor product of this with itself, right? So what would this be? So this would be nothing but 1 on here and everything else would be 0.
Hmm.
Do you see that?
Yeah.
This first block is basically nothing but this, because the first one is getting multiplied here and it's getting occupied in the first block here.
Okay, thanks.
I do that for all basis vectors. So here on the first slot, there will be 4 of them. In the second slot, there will be 4 of them. So there will be total 16 basis elements of the tensor product space. And they span the entire M4, as I mentioned here. So basically M2 tensor M2 is M4, right?
Yep, thanks.
Are there any other doubts?
I didn't get how the after you do the tensor product, how it spans the whole space. Can you repeat that part?
Yeah, okay. So you understand that when I take the tensor product of the first basis vector with itself, I get something in which only first entry is 0, first entry is 1, and everything else is 0, right?
Yeah, yeah.
Similarly, if I do this with, let's say, 0, 1 here, then what I'll get is 0, 1, and everything else 0.
Yes.
Right. And so you can see I can repeat this for all, I have to do this for all basis vectors, right? So if I do this, then this will be 0 and this will be 1. If I do
So each
this,
of these are the bases in that
yeah,
sense,
yeah.
right?
This
Okay.
is the basis, this is the set. And then we take the span. So we take all possible linear combinations of all of this. So basically you can think the basis set will have all these matrix units in which a single entry is 1 and everything else is 0. And then when you take linear combinations of them, you'll get the entire matrix space, right? You can have any complex number in any of the entries, because in the basis we have a single one in every spot and everything else is 0.
Yeah. Okay. Thanks.
Right? Okay. Should I move on?
Yeah.
One more small question, like,
Yeah.
why can't we just call them a complex vector space? What is special about a Hilbert space here?
So in finite dimensions, it turns out that there is nothing special about complex. So basically, you can call them vector spaces with an inner product. So this is an important thing to note here. So this vector space is endowed with the notion of inner product, which is basically, so this thing is a map which takes 2 copies of 2 vectors and then spits out a complex number, right? And this has lots of properties in the sense in the first slot is anti-linear, linear, and so on. So a vector space, so in finite dimensions, basically a vector space endowed with this inner product is a Hilbert space. But in infinite dimensions, this is not true anymore. So in infinite dimensions, you need to worry about notions of convergence and so on. So in infinite dimensions, things become a lot messy, and then you need, on top of this notion of complex vector space, you need to impose a notion of completeness, and that is the extra cherry that is required in order to turn a complex vector space into a complex Hilbert space. But in finite dimensions, it turns out that since everything is finite and the sums and all that we are considering is just finite, no extra notion of completeness is not required. And so in finite dimensions, we can interchangeably use the term complex vector space with an inner product and Hilbert space.
Right. Yeah. Thanks.
Okay. All right, let me now move on to the basics of quantum mechanics, right? Okay, so the point is that for any finite dimensions, we have a D-level quantum system in the sense that the system has, let's say, D energy levels that it can occupy. And to every D-level system, we associate a D-dimensional Hilbert space, so a complex Hilbert space, which will just be CD for us. This will be the space of all D tuples of complex numbers. And the states of the system are linear operators on this space. And we have seen that operators are nothing but matrices. So for us, and not all matrices deserve to be called states. There are some special properties are required in order for a matrix to be called a state. And but all the states of the system that we can think of, they all are linear operators acting on this D-dimensional space, and linear operators on the CD are nothing but matrices. So states are basically just D cross D matrices in finite dimensional quantum systems. And the special property that is required is that of positive semi-definite. So a matrix, a D cross D matrix rho is called a quantum state if it is positive semi-definite and there is some kind of a normalization required. So that is the trace normalization. So we require that some of the diagonal entries of this matrix should add up to 1. And just to recall, the notion of positivity. So a matrix rho is said to be positive semi-definite if this kind of an inner product is non-negative for all vectors V or kets V. So let's just break this down in terms of the columns and rows that we earlier discussed, right? So on the left we have a bra vector, right? So this will be like this, and in the middle we have a state row, which is the D cross D matrix, and on the right hand side we again have a column which is just this V again. And if you do your matrix multiplication, then finally you will be left with a complex number again. And the special property of positive semi-definite matrices is that this complex number is not only real but actually non-negative. So this should be non-negative for all vectors in the underlying Hilbert space. And another way to say it, another equivalent characterization is that if you calculate the eigenvalues of this matrix, I hope all of you are familiar with the notion of eigenvalues. You calculate the characteristic polynomial, right, determinant and so on. And then you calculate the eigenvalues. And if all of the eigenvalues turn out to be non-negative, we can be sure that the matrix that we started with was positive semi-definite. So this is the additional requirement for a matrix to be a quantum state. And for our purposes, this additional normalization is not really needed. The entire theory of entanglement and this entanglement does not really depend on normalization. We can choose it to be any K, or we can just get rid of it. And so that is what we'll do in this talk. And then we'll just ignore the normalization and we'll just call the space of all D cross D matrices, which are positive semi-definite. We'll just call it the set of all quantum states. So for us, positive semi-definite matrix, there's no difference between a positive semi-definite matrix and a quantum state, because we have chosen to ignore the normalization since it is not important while discussing entanglement. And very important properties of this. So simplest kind of states that one can think of are called pure. So these are of this form. So what you do is you take some vector on the underlying space and you form this kind of an outer product. And if you remember, you just write this in terms of the columns, right? So you have this row. No, okay. So this should be a column now. So this would be a column, and here this will be the conjugated row, right? And you can multiply it, and so you'll get a D cross D matrix here. And why is this positive semi-definite? You can simply take the inner product with V on both sides, right? And the property of inner product is that if you flip the two entries of the product, you get a complex conjugation. This is very clear from the definition. So this will just be the absolute value square of the inner product of the two vectors. And so this is non-negative for all V. And so it's clear that this is positive semi-definite matrix. And these are the simplest kinds of positive semi-definite matrices, which are called pure. And very important
Okay.
from linear. Is there a question?
Yeah, finish this, then I'll ask you.
Okay. So a fundamental result from linear algebra is that every positive semi-definite matrix, or for us, every quantum state, can be decomposed as a sum of pure states. And how can this be done? So let's say that we have a positive semi-definite matrix or a quantum state. We can write this in as a sum where, if you notice, these are the elements in the sum are nothing but pure states, and these are actually the eigenvectors of this matrix. And there is a constant sitting beside these eigenvectors, and these are the eigenvalues. And since the state is non-positive semi-definite, we have already seen that all the eigenvalues should be non-negative. And so this is the decomposition, and this is a non-trivial result. So in physics, usually it is always assumed that, just diagonalize the matrix, right? You just take the eigenvectors and eigenvalues, and this can always be done. But it turns out that this is very non-trivial. It's not. It's like usually the end result of a proper linear algebra course. So this is a theorem. We are not obviously going to delve into the proof of this, but the point is that every quantum state, we can split it up in the form of a sum of pure states, and where the constituents are nothing but the eigenvectors, the pure states formed by the eigenvectors, and we have the eigenvalues sitting beside them. And so we can actually, redefine these vectors by just incorporating the eigenvalues inside them. And if we do that, this just becomes, we can get rid of the factor, right, and just write them as this. This is just some subtlety. Yeah. So there was a question.
Yeah. So when you say you're ignoring the normalization,
Yes.
So are you saying, is it for making the math easier, or is there some physical meaning?
No.
Because
So the theory are completely unchanged. So, by the way, okay. So for instance, if you here, so anything that has the trace of rho is equal to 1, and so in the sense the sum of the eigenvalues is going to be 1. And so basically you are just reducing one degree of freedom. You can write one eigenvalue as 1 minus of the others. And this does not change anything in terms of when we talk about entanglement. So at the back of it, if you're uncomfortable with ignoring normalization, you can just assume that the states are normal.
cool.
It will not make any difference.
Yeah, because for me it doesn't make sense to define states without normalization at all.
So basically, the underlying mathematics is just completely independent of the normalization.
The math remains the same, right? Yeah, that's
yeah.
Okay, cool.
And so yeah, so for instance, in spectral decomposition, if you impose normalization, this condition will be imposed and nothing else will be changed. So if you can think of it, I'll talk about this when I talk about entanglement. But if you're uncomfortable, then you can assume at the back of your mind that everything is normalized, and I assure you that it will not make any difference on the mathematics or the theory. And okay, before moving on, let me mention a couple of properties of this set of positive semi-definite matrices. So this is
excuse me.
Yes.
Yeah, you said the density matrix can be diagonalized, but is it always convenient to diagonalize it? Even if, let's say, the space is infinite dimensional, is it convenient?
Yeah, so infinite dimensions, a whole lot of tricky things come into picture. So infinite dimensions, it is not true that states can be diagonalized. This whole theory of I would prefer to not go into continuous variables in infinite dimensions here. Infinite dimensions, the entire theory is very, very, very different from whatever we have in quantum in this finite dimension realm. So in infinite dimension, it turns out that not all these linear operators, which are positive semi-definite, can be diagonalized in the sense of diagonalization. And there is a lot of other technical tools that need to be, considered. There is a generalized diagonalization that one can think of, but the usual way of that we think of when we say diagonalization, it does not hold in infinite dimensions anymore. If anyone is interested in continuous variable dimensions, like the math of it, we can set up a talk sometime where I talk about what are the differences between finite dimensional quantum mechanics and infinite dimensional quantum mechanics. That would be an interesting talk. Let me just know if anyone's interested. So for us, I mean, I prefer to just keep within this nice regime of finite dimensions, because everything is very nice and simple here, relatively.
Even in finite dimension, is it always convenient to diagonalize the density matrix, or again there are some?
What do you mean by convenient?
Convenient, I mean, as you said that in infinite dimensional, it is of a different business. So
Yeah.
If somebody gives me density matrix, can I always diagonalize it and use it to
Yes.
calculate?
In finite dimensions, there's no problem. You can do it very easily. There are algorithms to do that on computers. You can employ singular value decomposition or all sorts of things. So in finite dimensions, it's a theorem. Given any quantum state, you can diagonalize it, and it can be proved in the sense that there's no ambiguity left. And this is usually the underlying assumption for any course in quantum mechanics. This is not really elaborated on more, but that is true in finite dimensions. You can do it without any problem. But in infinite dimensions, there is an existence problem, in the sense that there might not even exist a diagonalization for any given state. You get what I'm saying?
Yes. Okay. Thanks.
So in finite dimensions, you have a matrix. Yes.
You mean, I mean, there are matrices which are non-diagonalizable, right? So you mean to say that we can prove that only diagonalizable ones can be used in quantum mechanics, right?
So
as a
so this condition of positive semi-definite, this implies that the state can be diagonalized. In general, hermiticity is enough for diagonalization. So if a matrix is equal to the complex transpose conjugate of its own, then it can be diagonalized. And non-diagonalizable matrices are one for which more generally you can talk about normal matrices. But let's say that for us, if this hermiticity condition fails, if this is not the case, then you can easily find examples of matrices which cannot be diagonalized. But for us, so this positive semi-definite condition on quantum states, this is more than enough to guarantee the existence of diagonalization.
Okay, thanks.
All right. Okay, so I was just quickly going to mention that the set of all states that we have is what mathematicians call a convex cone, in the sense that if you have a quantum state, then what you can do is you can multiply it with any non-negative real number. This is a real number which is non-negative. I just write this as R plus, and this will again be a positive semi-definite matrix. And the second property is that you can take two positive semi-definite matrices and you can add them up, and then you again get a positive semi-definite matrices. These can be easily proven. And the picture to keep in mind is that of, let's say in the real plane in R2, we have the example of a convex cone would be something like this. Everything inside is. So you can take two objects here, you can add them up to get another vector which is here only. You can take a vector and you can multiply it by a constant to get another thing. So this is the geometry is that of a convex cone. You can think of it in R3 like this, like it extends infinitely. So the geometry of the set of quantum states is that of a cone, right? This is just for like a trivia, let's say. All right. So let me now quickly move on. So we talked about spectral decomposition, diagonalization, and so on. Right. Now we come to bipartite systems, where this phenomenon of entanglement will come into picture. So when we have two quantum systems, both of which are D-level systems, right? So for each system, we have a Hilbert space CD, right? And the axioms of quantum mechanics say that if you want to describe or model this dynamics of two particles at the same time, the underlying Hilbert space will have this tensor product structure. And this is precisely the definition that we earlier used, right? So we take the basis vectors, we multiply them in the notion of tensor product, and then we take the span. And so this is this Hilbert space of two parties. And again, as we know that the states of the system will be nothing but linear operators on this space. And so they will be, in this case, it can be shown that it will be the space of linear operators will be nothing but you take the space of linear operators for the first space, which will just be MD, the D cross D matrices, and for the second one as well, and you just take tensor product in the sense in the definition, the previous definition holds here as well. And so for bipartite systems, states of the physical system live in this tensor product of matrices. So this is, again, this is nothing but another matrix space which has dimension D squared. So this will be like the space of D squared cross D squared matrices, but with the underlying assumption that it is obtained in this way by tensor multiplying two individual matrix spaces corresponding to two different systems. Now, remember that not all matrices are states, right? We impose this additional constraint of positive semi-definiteness, right? So let's see how we can consider a typical state in this bipartite system. So let's imagine, again, we have two parties, right? So Alice and Bob, and let's say that individually they have the states of the individual parties is some rho and some sigma, let's say. And so since they are single party states, they will both live in D cross D matrices, which are positive semi-definite, right? And so the simplest way of combining them to give a product state is just taking the tensor product in the sense that we defined earlier. And so the result will be just this tensor product space and that tensor product state, and it can be easily checked that this will be positive semi-definite again. So this is like the tensor product of two positive semi-definite matrices is again positive semi-definite. You can check it by, like computing these matrix elements and showing that this is non-negative, but I'm not going to do that. And it's very easy. So this is just taking the product state of the two individual states of the two parties. And we can go a step further, and we know that this is a cone, right? This space of all the semi-definite matrices. So we can add stuff, and so that we live. So this is space is invariant under additions. So what we can do is we can more generally take a bunch of states for I equal to, let's say, 1 to n states on the Alice's side, n states on Bob's sides, and then on the result side we have n product states, and then we can sum them up from I equal to 1 to n, and this will again be a state of the bipartite system. And this is what we call, these are what we call separable states. So these are not entangled because by construction we have taken one state of one party and the other state of the other party, and then by construction we have just constructed a product state and then just summed it up. So, but the question is whether these are the only kinds of state that are possible, and it turns out that it is not the case. So in a single equation, if I want to describe the phenomena of entanglement, this would be it. So on the left hand side, we have the kind of states that I just described. I take the states of one party and the states of the other party and just take the tensor product, and I can mix them up in the sense that I can perform a summation. And they are what are called separable states because they're by construction local, right? Locally, we have taken the states of the two individual parties and multiplied them. But the set of all states that are possible in this bipartite system, which is we have the matrix space and the set of all possible positive semi-definite matrices in this bipartite space is much larger than just the product states. And so this is like a set inclusion, right? This is a strict inclusion, and you can think of it as in terms of cone. If I just take, let's say, on the first factor, we just saw that this is a cone, right? And on the second factor, this is again cone. So these are the cones of individual quantum states of the two systems. And what we are doing here to construct these kinds of state is we are doing some kind of a tensor product of this. And what we get here is another cone, which is what we call the set of separable states. But it turns out that the cone of all possible states in this bipartite system is much larger. So this lies within a larger cone, where this is the set of all possible matrices in the tensor product of the bipartite system. And the smaller one is what we obtain by just multiplying the individual states of the two parties separately. And so everything outside the smaller cone, but which is still inside here, this part is basically entanglement. So this is the equation to remember. You have two separate cones of quantum states for the two parties. You can mix them up in this fashion locally, and states that you obtain in this way are separable. But these are not all possible states of the bipartite system, in the sense that in this matrix space, there are other positive semi-definite matrices which cannot be written in this way. So this bigger cone is much bigger than the smaller one, and everything here is basically entanglement. Now let me just make this precise by just defining it in words. So a bipartite state of two parties is said to be separable if it lies in the tensor product of the two individual cones that I just described, right? Or in other words, you can find individual states of the two parties separately, such that the total state can be written as this mixture of product states. So if this is possible for any given state, we say that the state is separable. If this is not possible, then obviously we call the state entangled. And so this is the fundamental definition of entangled states. And if you can actually make it a bit easier in the sense that we can, spectrally decompose the constituents rho I and sigma I. So we know that every state can be written as a mixture of pure states, right? So we can write it as in this way, every rho I, and similarly every sigma I, we can write it in this fashion. So where this is J, this is K. And then when you put these expressions back here and you invoke distributivity and so on, the final expression will be something of this form. So the separable states are those which can be written as mixtures of product of pure states. So this is an equivalent definition of separability, which we will be using from now on. And these two are basically equivalent, which can be seen by invoking the spectral decomposition of the constituents. So this is the thing. This is the equation to keep in mind. A state of a bipartite system is called separable if a collection of vectors can be found such that the state rho can be written as a mixture of these product states. So is there any question on this part?
I have a question.
Yeah.
I was just curious because the definition I'm used to, what I have in mind, is has only one of these terms, rho. I mean, one rho tensored one sigma. So is that wrong? So in general, it's more you can have.
Yeah. So that is like a very special case of this. Like you're talking about this, right?
Yeah.
So this is like very special separable states in which we have just two constituents and you multiply them. In general, you can just add them up. Oops. You can take any. Okay, what's happening? I don't know. Let me just 1 second. You can take multiple copies of these product states and add them up, and you will not get any entanglement. It's like you are taking two states of two individual parties and then you classically mixing them in some sense.
Right.
So here I'm not considering normalization. So if you are considering the trace normalization, if you're uncomfortable with this positive semi-definite thing, then what will be the equation is that, so you'll have something like this. You have individual states like this, and then you will have some kind of a probability which will be used to mix them up, in the sense that these lambda i's will then be non-negative numbers which sum to 1.
Right.
So in that sense, you can think that Alice is in possession of n states, let's say rho 1, rho 2, rho n. Bob is in possession of n states, sigma 1, sigma 2, sigma n. And then they both are in agreement with a probability vector, let's say lambda 1, lambda n. So with probability lambda 1, Alice picks rho 1 and Bob picks sigma 1. And that's their state. But that's with probability lambda 1. Similarly, with probability lambda 2, they pick rho 1 and sigma 2. So and so on. So the combined state of these two parties would be this sum over lambda I sigma I rho I. So there is no entanglement present here. So even though there is a mixture, this is like classically combining the states with some probability.
Right. So since it's a classical mixture, we don't expect
Yeah.
there to be an entanglement.
Yes. So this is the most general definition of entanglement. And mathematically, it just comes by taking the tensor product of these cones. The tensor product of two individual cones, when you take the two individual cones and then multiply them, you get something which is smaller than the set of all possible states.
Right.
So that's why I keep emphasizing that this is like the main equation in one line. This is where entanglement comes into picture.
Yeah, makes sense. Thank you.
Okay. Are there any other questions?
Yeah, just for this notation, what is this cross notation on M, on the superscript of M?
Plus.
Plus.
Yeah, so this is the positive
this
semi.
plus sign of transposition.
Yeah. So this is here,
Okay.
right? I collected the set. This is basically the set of all quantum states, ignoring normalization. So this collects all D cross D matrices which are positive semi-definite.
Oh yeah, sure. Okay.
And so
this D square.
Yeah.
Yeah. This D square. Go to the next slide, please. Yes, this D square. So if I think of it in terms of qubits, let's say you have 2 qubits, right? And that will make a bipartite system. So this D square in that case will be 4 only.
4. Yeah.
I mean,
yeah.
So let me just let me just illustrate your example. So we have M2 and M2 here. Both of them are qubits. This is like M4. So a typical state of 2 qubits will be a 4x4 matrix. And you can think of it as a block matrix, right? So let me just give a quick example of a state. Let's just say that we have something like this, right? And so this is like some 4x4 matrix, right? In order for it to be a quantum state, this needs to be positive semi-definite, which can be quickly seen as computing the eigenvalues. Or in this case, you can actually write this in this way. So you have this column vector and you multiply it with this and 1001. So this is like a pure state where omega is this vector. So this is a pure state of 2 qubits. Basically, this is a 4x4 matrix. Okay, so this should be 1. Yeah. And let's suppose that someone hands me this state and I can compute the eigenvalues and just say that this is a positive semi-definite matrix. So at least this is a state. And if you want normalization, you can have half here and half everywhere else, right? But that's not really the point. I mean, that will not affect anything. So let's just keep it this way. And so what our question is to determine whether this is entangled or not. How does one do that? Right. So this is what I'll talk about next. But in general, if you have MD tensor MD, so this is basically matrices of size D squared. So this will be a big matrix of size D squared cross D squared, right? And you can check whether it is a state or not by just computing the eigenvalues and checking they are non-negative. And then the question is whether the state can be obtained, whether the state lies in the tensor product of these two. That's the problem. That's like the problem of detecting whether or not there is entanglement here. And this 2 qubit system will turn out to be a nice example in order to illustrate this point. And so for now, we can think of the problem like this. Someone hands you this 4x4 matrix. You know that this is positive semi-definite. And the question is, determine whether this is entangled or not. Right? So let's just see how can we do that. So the typical way is to use this notion of positive linear maps. So basically, what we do is we take this. So now this lambda here, this is a map which takes a D cross D matrix and spits out another D cross D matrix. It is linear. And the important property of this map is that this is positive. So basically, if you feed in a quantum state to this map, the output will be a quantum state again. So so it maps positive matrices to positive matrices again, and it is linear. So now let's say that someone hands you some, let's say that we have a separable state. So we have seen that the most general separable state, we can write it as a sum of mixture of these product states, right? And then let's say we have an example of okay, I don't know why this is happening. Let's say that someone hands you a linear map which is positive, and what we do is we apply this map only to the second part of the system. So this is called the partially applying this positive map on the state. And on the first part, we do nothing. Since everything is linear, we can just take this map inside the sum, and we get something like this. On the first part, nothing is changed. On the second part, this lambda acts on the states and spits out something which is again in MD plus, right? And this was again in MD plus to begin with, right? And so this entire thing is again separable, right? This is again MD plus and MD plus. So this is like, so the claim is that if rho that you have, if the bipartite state is separable, this implies that you can apply any positive map partially on this state, and the result will again be separable. In particular, this will be positive semi-definite. This will have non-negative eigenvalues. So this gives us a necessary condition for separability. So we start with something separable, and if we apply a positive map on just one half of the system, what we get as a result is again a positive semi-definite matrix. In particular, it is again separable. But this may not be the case if the input state is entangled. In general, let me just take this theorem quickly. This is like the fundamental result of entanglement theory. So here we just obtain an implication in one direction. If a state is separable, then for all positive maps lambda from MD to MD, partial action of this map on the state will again be separable. And the question is, can we conclude the reverse implication? Can we obtain the reverse implication as well? In the sense that if someone hands you a state and somehow you are able to calculate or compute that for all positive maps lambda, the partial action of this map on the state results in a separable state or result. So separability is not really needed here. You just need to ensure that this is positive semi-definite again. And if let's suppose that you are able to do that, this suffices to conclude that the state is separable. So the reverse implication also holds. And this is like the fundamental result which was obtained by the Horodecki family in 1996. And so basically the statement is that if you have a bipartite state, it is separable if and only if the partial action of any positive linear map on this state results in something which is non-negative, which is positive semi-definite again. Theoretically, this is like a nice characterization of separability. And how does entanglement come into picture here? So let's say that if we start with something rho which is entangled, let's say if rho is entangled, then by this characterization, there must exist a positive map from MD to MD such that the partial action of this positive map on the state rho, this is not positive semi-definite. Why does this hold? If there was no such map, then we are basically saying that for all positive maps, the partial action of this map on the state is positive, right? And then by this theorem, we can conclude that the state is separate. But this is not the case because we started with an entangled state, right? So this is like the most fundamental entanglement detection strategy. So the problem is, given a state, how do you figure out if there exists such a map which can detect the entanglement present? And this is where the entire problem lies, because this set of all positive linear maps is so large, you cannot possibly think of checking separately for each one. Right? Let me just illustrate this with one example of positive map that we are all familiar with, and that is, can anyone guess what that map is? No?
I can guess it, but I have a question before that.
Yeah.
I just wanted to ask, just to confirm, if you have a state, you wanted to check if it's entangled or not, and I have given you a map, and that map works in the sense that you act that on the partially on the state and gives you something that's not different. This map might not work for other states. Right?
Yeah,
so
it cannot. It might not. So every
that's
state,
also an issue.
Yeah, that's the whole point. If something works for one state, it may not work for any other state. That is the problem. There is no universal map which works for everything.
Right.
And if that was the case, then there would be no problem, right? We just have to check whether the action of that map partially on the state results in something positive.
Right.
And since that is not the case, that is where the entire complexity of the theory comes into picture. You need to, for every state, you need to check it on a case-by-case basis. For every state, you need to search this entire space of positive maps and see which one works.
Right.
And so let me illustrate this.
Satvik, I also have a couple of questions. Yeah. So first of all, you've been saying again and again that the number of positive maps is infinite. So by infinite, I mean, is it actually infinite or is it effectively infinite? I mean,
there are different kinds of infinities, right? So if you list all the natural numbers 1, 2, 3, 4, that kind of an infinity is called countable infinity. In the sense that you can put the numbers in a list and that list goes on forever. Then there is a different kind of infinity which you can imagine by considering, let's say, the set of all real numbers. That kind of infinity is one which cannot even be counted. You cannot list all possible real numbers in a line. And this infinity that I'm talking about here is of that kind. It's uncountable. It's so messy, it cannot even be counted. So it's uncountably infinite. And so there is no hope of checking this condition separately for each positive map.
Okay. Yeah. The second question is that, so see, I mean, I'm not very much used to thinking of quantum states in this density matrix formalism. So, I mean, what I'm thinking is, so we have been trying to build our theory, trying to detect entanglement only in this formalism. Somehow it seems to me that it should be easier to detect entanglement if you, revert back to the outer product decomposition and then try to detect if there's entanglement in the states. So, why does that strategy fail?
I don't get outer product decomposition.
See, a density matrix is just an outer product. Sum of outer products of.
He's talking about only vectors, I think, like only states.
Yeah. Okay. So any state row can be split up as a mixture of, let's say, this kind.
Yeah. So, decomposing our state into this form and then trying to detect entanglement, doesn't this strategy work?
I mean, it's the same problem, right? You have just split it up into parts. And so how does that help? How would this help?
Well, because
so the problem is, let's say you don't even split it. Let's say that you have a single pure state of this form, right? You have a pure state. And the problem of detecting, in order to detect entanglement here, you again have to do the same thing. You need to apply maps partially on this and check whether it is non-negative or something like that. There is no gain in decomposing it spectrally, because the problem lies the same. You have a matrix, you have a composite.
Yeah. It might have worked if the number of. Okay, yeah, I get it. I'm sorry.
Yeah. Other questions?
Satvik, so if how does the dimension play a role here? Okay, so I see that. So let's talk about a qubit case. For a two-dimensional Hilbert space, will there be still infinite number of positive maps?
Yeah, but it turns out that this qubit case is very, 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 very special, because I'll illustrate in the next slide. For qubits, the problem is solved essentially, because for qubits, there exists a very special positive map. And we need to check this condition for only a single positive map. And that ensures that for all positive maps, this will hold. So qubit case is very special. I'll talk about this next. But for all higher dimensions, d greater than or equal to 3, this is the problem. There is an infinite number of maps, uncountably infinite, and you have to check this for each one separately.
Okay.
I think Anubhav's question was for the qubit case, how many maps are there? Was that?
It's uncountable. You cannot count them.
It's uncountable. Yeah.
So how many numbers are there on the real line?
Yeah, I get it.
It cannot be counted.
Yeah. Okay.
I mean, I just wanted to know whether there's a dimension dependence there.
Yeah. So you can imagine that. Okay. How do you? So a linear map from CD to CD. We say that this is like a matrix, right? So this is a D cross D matrix. So if you're now going one step further and considering linear maps from MD to MD, then this will be a D squared cross D squared matrix basically, right? And any entry here inside can be any complex number.
Yeah.
And with the additional constraint that this constraint should hold, in the sense that it maps positive matrices to positive matrices. But still, you can imagine that it's like a matrix. Any positive linear map is a big matrix. From any positive linear map from MD to MD is basically nothing but a D squared cross D squared matrix.
Mm-hmm.
It acts on a matrix and spits out another matrix. And the constituents of this matrix inside here, it can be any complex number, right? And for even if it was a single complex number, there are uncountably many complex numbers. And so there are like d to the power 4 complex numbers here. And as dimension increases, the number of complex numbers increases as d to the power something. So it's
Shouldn't it be a D cross tree matrix only, because otherwise multiplication will not hold, right?
No. So this is not matrix multiplication. This is so what you do is, this will be a column vector again. So this matrix will be represented like as a D squared cross 1 column vector. So what you do is, you have a D cross D matrix, and you take the first row and you arrange it here. You take the second row, arrange it here, and so on. Do it for all rows, and then you get a long list of numbers. You're basically reshuffling the entries, and then the map can be thought of as a matrix which acts on this column vector and spits out another column vector. It's not really important here. The point is that if there is any linear map lambda between two vector spaces, this map can always be represented in the form of a matrix. Let's say both of them are d-dimensional. So this map can be represented as a D cross D matrix. So in the case of, if it is a map from MD to MD, then the dimension of this vector space is D squared, right? And dimension of this vector space is also D squared. So this map can be represented as a D squared cross D squared matrix. This is true for all vector space, any linear map between a vector space. All right, so let me talk about
a second before you continue. You have assumed that lambda is a positive map, but not necessarily CPTP, right?
Yeah, so I have not introduced completely positive anywhere.
Right. So if lambda is not CPTP, then it's not physical also. And if it is not physical, this then is only something that you can do on paper. You can't do this in an experiment.
Okay. That's a wonderful question. And so basically the point is that if you need to implement this test in a lab, you need to, so there is a one-to-one relation between linear maps from MD to MD, and okay, so that will take a couple of more yeah, okay, let me just state here. So if you have a linear map from MD to MD, what you can do is you can associate to it a state or a matrix in this way. In matrix in MD tensor MD, which is defined as in this way. So what you do is you take this kind of sum. So basically, you act on the base matrix units that we have by lambda, and you tensor product it with the same matrix unit, and you sum it up. And this matrix is then something in MD tensor MD. And this mapping, so let's call it J lambda, and the map which takes lambda to J lambda, this is a 1-to-1, and onto this is a bijection. So there is a 1-to-1 correspondence between linear maps from MD to MD and matrices in MD tensor MD. And the nice thing is that when one computes the matrix in MD tensor MD corresponding to any positive map, the result that you get is Hermitian. Hermitian in the sense that conjugate transpose is its own, right? And then in the sense of quantum mechanics, this thing is an observable, because in quantum mechanics, every operator, a Hermitian operator, is like an observable, right? And then basically the condition of partially acting on this on any state by this map and obtaining something which is not positive semi-definite, this translates into saying that trace of this row that you are considering the input matrix with this observable J lambda, this is less than 0. So basically what this requires some derivation. So, but the point is that experimentally, if you want to determine whether or not a state is entangled, you construct these kind of witnesses. So these are called entanglement witnesses. So basically they are observables in the proper sense of quantum mechanics. These are Hermitian matrices, and you can, this is like the expectation value of that observable given the state rho. And if lambda is a witness for this entangled state, in the sense that this equation holds, which holds only on paper, as you said, right? The corresponding witness operator, the expectation value of that witness operator in this state rho will be negative, and that can be computed, and that is how usually things are done in lab. And there are other tests in lab like Bell inequalities and all sorts of other stuff, but this is like the basic mathematical underpinning of how entanglement is detected. So these are called witnesses, both of them. Let's say if this holds for any rho J of lambda, this is said to be the witness which detects the entanglement in rho. Right. So let me move on quickly to the transpose. Yeah, so I was talking about the quintessential example of positive map, which is that of transposition. So what you do is you just take a matrix and you compute its transpose. And transposition is positive. Why? Because you can compute the eigenvalues and say that they are unchanged, basically. And so it's a positive map. And so since it's a positive map, this provides us with an entanglement detection test. And as we saw earlier, so basically what we do is we have a state, we apply this transpose map partially here. There can be two possibilities. This can be not positive semi-definite. If that is the case, we can straight away deduce that there is entanglement present, right? If it is positive semi-definite, then we can conclude nothing. This may be entangled, this may be separable, but you need to go on and check for other positive maps and so on, right? So this transpose, this provides us with a convenient linear map, which can be used to detect entanglement in lots of states, in the sense that you take the partial transpose, this is called the partial transposition. And if the partial transpose of this map results in something which is not positive semi-definite, the state is entangled. And but there are states for which the partial transpose may be positive, but still there may exist some other positive map which detects the entanglement. So that those states are called PPT entangled. So even though the partial transposition is positive, the state is still entangled. And this means that we must have some other positive linear map must exist which detects the entanglement in the state. So we have this kind of a picture here. So in the middle, the smallest set that we have here, this is the set of all separable matrices, let's say. This next circle here, this is the set of all states which stays positive under partial transposition. And this outer thing is all possible states. So clearly, separable states, we have seen that they only form a very small part of the set of all possible states. And we have also seen that if the state is separable, then obviously the partial transposition will be positive. And so the states of separable states will lie inside the set of states which stay positive under partial transposition. And everything here outside in this set, this will correspond to PPT entanglement, in the sense that even though the states are PPT, they are not separable. They are still entangled. And it has been a topic of tremendous interest to find examples of states which are PPT entangled. They can use our resources in several procedures and so on. And till now, I mean, they are known to exist, but there are very few examples which are explicitly known to be PPT and entangled as well. And you can easily, if you check some literature on entanglement, you can find papers called like finding new kinds of PPT entanglement and so on. So basically, they find examples of states which are PPT, but for which some other positive map, which is not transposition, detects the entanglement in that state. And they have resources, and so that they can be used as resources in cryptographic protocols and secret key sharing and so on. So I'm not going to go into the details of that. But this is like an open question of unearthing new kinds of states which are PPT but still entangled. And we will see that the connection with graphs later allows us to construct these kind of states effortlessly. And this is the theorem that I was talking about earlier for the qubit case. So it turns out that for the qubits, if you have 2 qubits and you have a state for 2 qubits, you need not do the entire procedure that I just described. This transposition it turns out to be very special in this case, in the sense that if the state is positive under partial transposition, then that state is guaranteed to be separable, and the other way around as well. So in qubit systems, separability is equivalent to positivity under partial transposition. And so if you're just living in qubits, and if you're just dealing with qubits, the entire thing is very easy. You just need to take the state and check whether its partial transpose is positive or not. So the 2 qubit state that we earlier considered, this matrix, right? This is a qubit matrix, and we have just seen that you just need to apply transpose on one of the parts of this state, and you can very easily see that this transpose will basically just act on the blocks separately. So if it was the whole transposition as a whole on 4x4 matrices, you'll just basically switch the rows and columns, right? But since this is partially acting on this state, the effect of this transposition would be to transpose each of these blocks separately. I mean, it can be shown easily. I'm just not doing that here. And then once you do that, what you see is that on these 2 blocks, basically state is unchanged. But here, this 1 goes here, and so you get 1 here and 0 here, and similarly 1 comes here, and this is the state that you get. And it is easy to see that this block will contribute a -1 eigenvalue here. And so when you act on this matrix by transposition only on one system, you get something which is not positive semi-definite. Why? Because you can explicitly compute the eigenvalues and see that there is a -1 eigenvalue present. So in qubits, everything is very nice and simple. And this is a very deep result and complicated proof. It's not at all trivial to show that this is the case for qubits, and it requires a lot of effort. And so obviously I'm not going to talk about that here, but I just wanted to mention it, that for qubits, the problem is essentially solved. But as soon as you get in dimension 3 or larger, you get into trouble. All right. So this was like part 1. It got extended a bit. It's already 1.5 hours. So I haven't even come to topic of my research. This was all entanglement theoretic background. So maybe we can take a break for. Huh?
Yeah, maybe we can take a break, of course. And I have a question meanwhile.
Yeah.
We'll go to your previous slide.
Which one?
Yeah, this one. So you're saying that it's about qubits, right?
Mhm.
So I think I'm confused about it. So the qubits and bipartite system, are these the same things? I think these are different, right?
So
Or
here qubits, there are two qubits
so two
basically.
qubits.
Yeah, for two qubits, the separability is basically the same as PPT.
Yeah.
And if you
Okay.
have qubit, and higher level systems, composite systems, then things get messy.
All right. So here we have two qubits, and this
Yeah, for
theorem
two
is for
qubits.
two
Yeah,
qubits.
yeah. This theorem is for two qubits.
Great.
So for qubit, this diagram will this PPT set will collapse into the
With
set of qubits, and there will be nothing else. And that's why in qubits everything is nice, but as soon this diagram will hold in the sense that this will be something which is not empty, where as soon as you get in dimensions 3 or higher. So qubit, it would be the simplest case where PPT entanglement exists.
I just had one question, just on the definition. So in this diagram here, so PPT entangled states are both the yellow separable ones and the part outside. So I just wanted to confirm. So
PPT entanglement is which stays outside this separable circle, but still inside PPT.
okay, so PPT entanglement is essentially those states for which the PPT test fails.
Yeah, basically.
Okay, so if the PPT test, is successful, that means it's just separable.
No, the PPT set,
No.
Oh, okay, so if it is successful, it means they're entangled.
Yeah, by success, if you mean that when you apply it partially, you get something which is not positive semi-definite, then
that doesn't say anything, right?
No. If it is not positive semi-definite, that is a success, right? You are successful in detecting entanglement, and if that is the case, you have a state which is detected by the transpose map. But that may not be the case. You can apply the transpose map, and still you may fail in the sense that the state output may be positive semi-definite, and in that case, you need to continue doing this procedure. And at some point, at some higher point, if you started with an entangled state, then there must exist some map which detects the entanglement, and since the transpose test was successful, we say that it is PPT, it is positive under partial transposition. But at some other point the test fails, and so there is still entanglement here, but that cannot be detected by the transpose map. That is the definition of PPT entanglement.
Okay, makes sense. Yeah, thanks.
Someone is raising the hand.
Yes, Shivanshu.
Yeah, am I audible?
Yes, you are.
Yeah, so in the introduction, you mentioned that there's no classical algorithm which
Yeah.
can efficiently detect whether a given system of qubits is entangled or not.
Sure.
So is it because like no classical algorithm has been developed so far, or is it like a theorem like that you cannot do it on a classical computer? Like which
So
case is it?
This is like a result in complexity theory. So as I said, if you wait for long enough, then even classically, you can detect entanglement. But the trouble is that this long enough might be a billion years. And then it doesn't make sense to wait for that long, right? And so even classically, so there's a package on MATLAB called QuetLab, where there is a function called is separable. So what that function, you input a bipartite state, and then you apply this is separable function, and then it tells you whether the state is entangled or not. But if you apply that on your computer, you can do that this evening, then you can very quickly see that for most of the cases, the test will run for like 10 minutes, 20 minutes, and half an hour. And then there is a built-in a counter in it, which just terminates the algorithm if it takes more than 30 minutes and so. And then it just says that the algorithm cannot detect whether it is entangled or not. So even classically, there are algorithms which, if you run them for long enough, will be able to tell whether there is entanglement present or not. But the point is that you may need to wait for a billion years.
Okay, so to successfully do this, like in the human scale time, so you need another like a quantum computer to do this.
I mean, yeah. So that's I think someone else also asked this in the beginning, whether there exists a quantum algorithm which can do this quickly. And as far as my understanding is concerned, I'm not aware of any quantum algorithm which can do this in, let's say, polynomial time or some reasonable time frame. I might be wrong, but I'm pretty sure that that is not the case, even if you consider quantum algorithms.
Okay, yeah, thanks.
Okay.